Okay, good morning. This is March 5th, 2025, 9:43 a.m. Pacific time. So I want to show you the syllabus and this schedule, right, of classes we are writing here. Oh man, the exam is going to be next week, huh? Let's see here. We're writing here, we're going to finish lab 1 and 2. I also want to do some lecture. Now, I want to check with you about the exam, okay? A student of mine asked me to postpone the exam another week. What do you think? What do you think? I want to check with you before I do that. Okay, it will give you more time for you to study, right? It shouldn't. We started when we start 10th of February. Yeah, it's not bad. We can, we can, put this exam that would be next week for the other week. What do you think, right? I'm gonna go back to that because we have only 12 students right now. Oh yeah, that's right. Gotta share the screen. Thank you, Ramon. And here you go. That's the screen here. Here you go. Wednesday. That's March 5th. Lab 1 and 2, and then continue the electric fields 1 and 2. We're going to do that today. Lab 1 is very similar to lab 2. It's just a different electrode configuration, so you can do everything today here. Now, I also want to continue covering capacitance, right? Capacitance. And, I'm putting out there for everybody, okay? You don't have to decide right now. And I'm going to go back to that. Postpone the exam by 1 week. If you don't do anything, the exam is still going to be next Wednesday, the 12th of March. And otherwise, we can put it for the 19th of March, okay? Think about that. I have already heard from 2 students, right? And later on, I'll get back to that. I'll get back with you on that. And let's get our notes here. Go. Postpone. Okay, one more student postponing. That's good. The more I hear from you, the better. 3 students already, right? And right in here. Insert. Today is March 5th, 25. That is Wednesday. Week number. Week number 4. Week number 4 for a total of 17 weeks. A total of 17 weeks, okay? Okay, I'm getting more students here asking me to postpone. So let me document here in my notes. Right now, the first exam is scheduled for March 12, 25, next week. And I was asked to postpone it to postpone it. Yeah. Postpone it one more week to March 19, 25. Okay. And more students here coming in. So let's see. So think about that. When I do the roll, I'm gonna ask you again, okay, whether you want to postpone it or not. or it doesn't, doesn't make any difference, right? So what I was doing here, I was calculating the capacitance of different geometrical configurations, okay? I did just for the parallel plate and the spherical shell, okay? So last time we did the following. One, we started capacitors. Two, defined a quantity related to a capacitor called the capacitance. Derived the capacitance for two different capacitors. For two, let's see, for two different types of capacitors. The parallel plate capacitor and the spherical shell capacitor. Okay. Again, it's difficult to emphasize that, but capacitors is a very important type of device used in electronics, used in electricity. Okay, so don't underestimate the simplicity of the capacitor. Don't underestimate it. Let's go also to our book, Wiley Plus. Login. This one here. And Wiley Resources. Launch. Capacitors. Okay, so here you go. Here's a drawing of a multimeter, something that I have already told you, right? And the multimeter is measuring the potential difference, the electric potential difference between those two plates. It's getting like 1.2 volts. Okay, so that's what we are doing here. And here's the relation between capacitance, electric charge, and voltage. Right? The unit of capacitance is the farad. Here we have a transistor, by the way. Remember, we're not going to talk about transistors, okay? In this course, transistors is for something else, for a course that's more advanced. Is part of a RAM chip used in computer memories. Okay, transistor capacitor combination is part of a RAM chip used in computer memories. So the chip that the memory chip, right? Random access memory chip. So whenever you combine a capacitor with this transistor here, which by the way is just a switch, okay? It's just a switch. It's a switch with three, 1, 2, 3 leads. Okay, capacitor has only 2 leads, but the transistor has 3 leads. Okay, we're not going to elaborate on that because But it works just like a regular switch, the same switch that you have there at home that turns on and turns off a light. That's what this transistor does. This transistor turns on and off depending on certain conditions. Okay, here we go. We have the capacitor with parallel plate capacitor, and then parallel plate capacitor with a dielectric. When we insert a dielectric in the capacitor, the charge doesn't change. The charge doesn't change because remember, this charge cannot jump from this capacitor to the dielectric. Okay, that's why we insert a dielectric here. So no charge leaks out from the capacitor. So no matter whether you have just air or vacuum here inside your capacitor, the capacitor is not going to increase or decrease the charges, okay? It's not going to increase or decrease the charge because we're inserting a dielectric. Because we're inserting a dielectric, there's no way that charges will be transferred between the plate and the dielectric, okay? Although the charge does not change, other things change. Other things change. And we saw that the voltage changes, the voltage of your capacitor changes, the electric field changes. First, the electric field, right? From the electric field, you'll find out that the voltage also changes. And one more thing that I told you that changes is the capacitance. The capacitance also changes. And there is also something else that changes. I was going to talk to you about that, but then we run out of time, right? Here you go, that's the electric field. The electric field decreases by a factor kappa. This factor kappa is a dielectric constant that depends on the type of a dielectric. I mentioned to you the dielectric constant of the vacuum and the air, they're almost the same. Okay, the difference is so small that we can neglect those two numbers here. And then we have the dielectric constant of other devices, Teflon, benzene, paper, ruby mica, neoprene rubber, blah, 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 right? And water. Here we're talking about pure water, deionized water. Okay. Parallel plate capacitor filled with a dielectric. We found that out. We did that in class. The capacitance increases. The voltage decreases, the electric field decreases, but the capacitance increases. Okay. And that can be proven mathematically. And here, one of the applications of the capacitor. Here you go. My keyboard, the one I have here, and everybody else has, right? They use capacitors to map which key we are pressing in the keyboard, okay? One kind of computer keyboard is based on the idea of capacitance. That's just one of the possible applications of capacitance, of a capacitor. There are many other applications of capacitors, okay? There's just one of them. Each key is mounted on one end of a plunger, and the other end is attached to a movable metal plate. See figure 19.19. Here you go. Movable metal plate, plunger, and movable metal plate right in here. Here's the key B, right? For the letter B. Let's see. The movable plate is separated from a fixed plate. Okay, that's the movable plate. That's the fixed metal plate. What's this movable metal plate and what's this fixed metal plate, right? The two plates forming a capacitor. See that? Two conductive plates. Okay? The two plates form a capacitor. When the key is pressed, the movable plate is pushed closer to the fixed plate and the capacitance increases. The distance, right? The distance between the capacitors decrease. If the distance decreases, the capacitance must increase, right? So go back here to our result of the capacitance for a parallel plate capacitor. Here you go. Let's see. Further down, baba. Here for the spherical capacitor, right? And here is for the parallel plate capacitor. You decrease the separation of the plates, and consequently, the capacitance increases, right? The moment we press the key, we have this variation in the capacitance. We have the variation in this capacitance. And let's see, capacitance. Electronic circuitry enables the computer to detect the change in capacitance. So you have an electronic circuitry that's monitoring the capacitance of every key in your keyboard. Okay? Thereby recognizing which key has been pressed. The separation of the plates is normally 5 millimeters. 10 to minus 3 meters is 5 times 10 to minus 3 meters is 5 millimeters, but decrease by a 10.15 millimeters when a key is pressed. The plate area is 9.5 10 to minus 5 square meter, and the capacitor is filled with a material whose dielectric constant is 3.5. Okay? Determine the change in capacitance that is detected by the computer. Let's do that as an example. That's a good example. Okay? Let's go here. I'm going to write that down. Example. And then we go back. Oh, let's see. I also have to put here what happens when we place a dielectric between the plates, when we place different, right? Different dielectrics between the plates of a capacitor. Okay. So example 11, right, of the book. Let's see here. Yeah, example 11 of the book. So what you have to know to solve this example. Okay. The separation between the plates of a capacitor is 5 millimeters. Okay? When we depress when we let's see, when we compress, let's see, there is a, here you go, there is between the parallel plates of a capacitor, let's put here, parallel plates of a capacitor is 5 millimeters. There is a dielectric material between these plates with a dielectric constant of what's the dielectric constant? Remember, the dielectric constant has no unit whatsoever. Dielectric constant of 3.5. Dielectric constant of 3.5. Oh, my escalator is trying to get in. Okay. When we compress the two plates, okay, their separation decreases by 0.15 millimeters. Is that right? You just thought, yeah, 0.15 millimeters. Okay. The area of the plate, okay, the area of the plate is 9.5 times 10 to the minus 5 meters square. The area of each plate is, let's go back again, already forgot. 9.5 times 10 to minus 5. I'll put it on this side. So I can refer more quickly. 9.5 times 10 to minus 5 square meter. Okay. Find the change in capacitance. The change in capacitance. Find the change in capacitance. One more student. Solution. So let's take a look at our example of calculations. Okay, parallel plate right in here. We're gonna need that. Okay. That's the formula that we're going to use for the parallel plate capacitor, but I'm gonna use the C naught notation just to remind you that this is the plate with air or vacuum. This is the capacitor with air or vacuum between the plates. Okay. And we also know that when we insert dielectric material there, the capacitance increases by a factor kappa, like that. Okay? So we can go ahead and calculate. It's always good to have a numerical sense of those quantities, okay? That's the capacitance without depressing it, without depressing the capacitor. Let's calculate how much that is. Okay, I recommend that you do your math equations in a spreadsheet, okay? I think it's far better doing that with the spreadsheet than with your calculator. That's my advice. Okay, so here you go. We have A in meter square. We have D in meter. We have kappa that has no unit whatsoever. By no unit, I mean a unitless unit is the number 1. Okay, what else do we need? We need to calculate the capacitance. We will also need that epsilon naught. Epsilon naught. And epsilon naught had that special unit that I'm going to get for you soon. Okay, fonts right in here. That's what I want. Subscript. I want also change this one to symbol. Okay. Capacitance. So let's get everything that we need. Right? Oh, I need the make it nice. This one too. Here you go. Superscript. Right? And I'm going to boldface everything. Here's 3.5, right? That's what I remember. This one is what, 5 millimeters? 0.005 meters. And this one here is a small number as well. Let's take a look at this number. Area 9.5 times 10 to minus 5. 9.5 times 10 to minus 5. Okay. And then we gotta get the epsilon naught. Okay, first we're going to calculate the capacitance without compressing it, 5 millimeters. And then we're going to calculate the capacitance with the compression. Okay, so here we go, and that's gonna put it here, delta D. Okay, delta D. Symbol. Here you go, delta D. Initially, you're going to calculate for no compression, and then, we calculate for the -3, right? A tenth of a millimeter. The other numbers don't change. What changes is the delta D, and then we have to put an equation for the capacitance, okay? So epsilon naught, what's the value of epsilon naught? Let's take a look at the value of epsilon naught. 8.85 times 10 to minus 12. And the unit is a complicated unit that's given by C squared over Newton square meter square. Let's see if we can get it. No, it didn't work, did it? Yeah, this one worked, but not the other. Let's try it again. Ah, so odd. It's not working for some reason, so I have to do one by one. Superscript and superscript. Okay. Doesn't change for the other configuration. And here I'm going to put capacitance in farad, right? Calculated. And let's calculate that. First is the kappa. Kappa is the first one that goes there, times the area divided by D. And by the way, divided by D. Okay? And don't forget minus my delta D, right? I'm compressing. And let's see if I forgot anything. There's one more term, which is the epsilon naught. Let's take a look at the equation again. So we don't miss anything. I'm gonna put side by side here, so it make it easier for us to refer. Okay, and right here. A, the area, the kappa, epsilon naught. Okay, I need to multiply by epsilon naught right here, divided by D. Okay, that's what I'm getting. I'm getting 5.89 times 10 to minus 13 farad. Let's see if I did everything right. Yep, I did everything right. It looks like I did. And now I can click and drag. And now we are going to get a capacitor with a separation that is slightly less. It's slightly less, right? And you can see that the capacitance increases. Okay, the capacitance increases. And the change in capacitance is going to be L. L. capacitance here. And farad, delta capacitance. Okay? It's gonna be one minus the other. That's what the book has. 1.82 times 10 to minus 14 farad. Okay? There's a very small change here. Now, let's see what the book says. Okay, they said we're getting a different number here. Let's see what's going on. Did I multiply by 3.5? 3.5. Area, let's see, area. 9.5 times 10 to minus 5. Yep. Meters squared. 8.85 times 10 to minus 12. Okay, 9.5. Okay. It's getting 19.6 picofaraday. Why is that? Let's see, why is that? I'm getting different, very different. Let's see why is the difference so large, right? 5 millimeters. Oh, wait a minute. Let's see here. Oh, okay. The separation of the plates decreases to 0.15. Okay, so I'm making I am misinterpreting it. It's not that there's a difference in 1.5. No. It's not a difference in 1.5. It decreases. It actually decreases. Okay, so it's a big decrease in the capacitance. Okay, so let's redo the math. Okay, so let's take a look. I misread it here. Okay, the separation of the plates is normally 5 millimeters, but decreases to. Okay, it didn't say decreases by, right? When a key is depressed, that's a huge, that's a huge decrease. Okay, that's 10 times less. 10 times less than before. More than 10 times less than before. Okay, so that was the mistake that I made. Okay, now I can fix it, right? And can calculate now. Let's see. A kappa, A epsilon naught divided by C2 only. We don't need that term anymore. C2 is the diameter. The diameter, no, the distance between the plates, right? That's the value of the capacitance before you depress. Now, that's the value of the capacitance after you depress. But we're still getting a 1.5. Oh, let's see. Oh, gosh. I put it in the wrong place. It's this one here. Okay. Yeah, here you go. I got to change it too. Let's see. This one is supposed to go here. Okay, and this one goes here. Okay, now we get it. Do you see the mistake that we usually make? Even with this Excel spreadsheet, but Excel is spreadsheet, I made two mistakes, right? One mistake, I misinterpreted the distance between the plates. I thought that they were being compressed only by 0.15 millimeters, when in reality, they are not being compressed by 1.5 millimeters, 0.15 millimeters. They are actually becoming 0.15, the distance, right? Becomes from 5 millimeters to 0.15 millimeters. So it's a huge compression, 10 times, more than 10 times the original distance. So that was one mistake that I made, right? the other mistake that I made. I put this number right in here, right? Instead of here. And now I'm getting the answer of the book. 1.9. 1.9 times 10 to minus 11. Yeah. That is, he's getting 19.6, okay? But it's a very small difference. You don't have to worry about, oh, wait a minute. No, this one here. I gotta, here you go. 1.96, yeah. Just like I got. And this thing is 19.6 picofarad. Okay? So that's, now we're gonna talk about energy storage and capacitor. This is an example in the book. That's a very good example because it has a practical application, real life application. Now, let us see what happens to the energy. And by energy, I mean the potential energy in a capacitor whenever we insert a dielectric. Okay? Insert a dielectric. And in order to solve this problem, we have to go back to the derivation of the potential energy in the capacitor. Okay, let's see. Energy, 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 U, we want the U, right? And I gave you 3 different formulas for the potential energy. Another student coming in. Potential energy. What happens? Okay, here you go. That's the potential energy here. Okay, so here you go. Let's get the 3 different formulas for the potential energy of a capacitor, parallel plate capacitor. Okay. And let's just use this one here. Okay. You can use either of one, either of the three, all right? Half Q squared over C. Already told you that the charge in the capacitor is not affected when we insert a dielectric inside the plates, inside the capacitor. Okay? However, we do know that the capacitance changes, increases, right? Capacitance increases. So I'm gonna use a simpler notation here. Instead of delta U, I'm gonna use just U. Okay, U naught without the dielectric, just with vacuum or air in between the plates. It's gonna be like that. With the dielectric, we use a different notation, right? Like that. Like that. Charge doesn't change, but capacitance change. And if capacitance change, the potential energy is also going to change. The capacitance increases, right? Capacitance here is going to increase. Consequently, the potential energy is going to decrease, right? So it is going to decrease by a factor of kappa. write that. So here you go. Gonna be like that. U naught divided by kappa. Okay, that's how much it decreases. You lose energy when you insert the dielectric in there. Okay. Lose energy. And then we also have one more equation that I want you to know. Right? So here you go. There are, more than one equation for the energy, right? Can also be written down in terms of C V squared, right? That's another expression for my capacitance. And if you repeat for that, you're also going to get the same result here. But I'm going to use this equation to calculate something else. Now, let us calculate the energy density of a capacitor. Okay? In order to calculate the energy density, it's easier to use this equation right in here. Okay? First, calculate the energy, right? The energy of a parallel plate capacitor. You already know that is given by kappa A epsilon naught over D. Like that. I'm going to put that between parentheses. And now we have to write down the voltage too, right? The voltage of a parallel plate capacitor, I'm going to put it between parentheses. We already know that goes with the electric field, E times D. Is linear with the distance from the plates, okay? Remember that? And then let's keep on calculating here. First the energy, then you're going to calculate the energy density. E squared, we end up having E squared here. We end up having D squared here. Like that. I don't need my parentheses here anymore, any longer. D is going to cancel out with D. D is going to cancel out with D. Kappa A epsilon naught. And that's what we get for the energy in terms of the geometrical parameters of the capacitor, but also the electric field, okay? It goes with the square of the electric field. So do you see that? Goes with the square of the electric field. And the epsilon naught, I'm going to put here next to the kappa. Okay, and notice what we have here. We have the area times the separation between the plates of the capacitor. Okay, do you see that? The area times the separation between the plates is actually the volume of the capacitor. I'm going to write it down like that, V. Okay. So that's going to be, it shouldn't be not here, it should be U. Okay. Since we're putting the kappa there, let's write down the U. Not, it should be U naught for kappa equal to 1. So let's write it down here. The final result for the energy Okay. The larger the volume of the capacitor, the more energy it stores. Okay. The more potential energy it stores. The larger the dielectric constant, the more you store energy as well. And the larger the electric field, the energy goes as the square of the electric field. If you manage to put more charges there in your capacitor, the electric field is going to increase, right? The more charge you put in there, the larger is going to be the electric field, but the increase is going to be with the square of the electric field. So you might be better off just adding more charge to your capacitor to increase your energy. And then there is one more thing that you can do, okay? What about the energy density? What is the energy density of the capacitor? Okay, of the energy density, the energy per unit of volume, right? Energy density or the energy per unit of volume of the capacitor. All you have to do is to divide both sides by V, right? When I divide by V, the V on the right side is going to disappear. I'm going to emphasize here that we are dividing. This V here disappeared. And this ratio that you have right here, we usually denote it by another letter. Usually denoted by the letter mu. Okay, and we put a subscript here of E for electric density of energy. The energy due to the electric field. The energy due to the electric field, okay? We get a similar formula for the magnetic field. We do get a similar formula for the magnetic field, and it goes with the magnetic field square. That's what we have for this chapter 19. Okay, I'm going to stop here. And let me put a list of the sections of this chapter that you have to worry about. Okay, so electric potential energy and electric potential. That's what we covered so far. Let me put also chapter 18 here for you. Origin of electricity, charged object and electric force, conductors and insulators, Coulomb's law, electric field lines, Gauss's law. And then we did cover potential energy, electric potential energy difference, electric potential energy difference, electric potential difference by point charges, equipotential surfaces, okay, capacitors and dielectric. For now, we are going to skip those two sections. You don't have to worry about those two, okay? Skip and skip. 1032. Let me see if you have any questions so far. Okay. Let's take attendance. And just a reminder for those.
Excuse me.
Yeah?
Do you think you could scroll up to the page before this one so I can see the formula again?
How far? How far?
Right there. Right there, right there. Thank you.
Capacitance, right? Ideally, we should be memorizing those things, but sometimes it's very difficult to memorize everything, right? The voltage is the electric field times the distance, right? the voltage, the electric field is uniform, but the voltage, no, the voltage changes from one plate to another one. As you move from one plate to the other one, as the voltage is going to change. So, and it's directly proportional to the electric field and the distance between the plates. Here, the voltage that I'm talking about is the voltage between the plates, okay? The voltage, electric potential between the plates. Let's see if I have a page. I don't have page number here. Let me put a page number. Okay, we're already on page 36. Can I move down now? Did you copy everything already?
Yes, you can move down. I did have a question though.
Yeah.
So, are there two formulas to calculate the energy density of a capacitor?
Okay, now there's just one
Capacitor.
formula, right? Here you go. Let me here write that down.
Oh, it's just that you wrote the same sentence, I believe. Because this question right here on this page says, what is the energy density of the capacitor? And the other one said the same thing. So I was kind of,
Okay. This one is the energy density, okay? This one is the energy density. This other one, maybe you might be talking about this other one here, right? This other one is just the
yes,
energy.
that one.
It's just the this one is just the energy, okay?
Okay, but then could you erase energy density in the sentence before that formula on page 36?
Let's see.
Or it
And
says, now let us calculate.
now let's go. Okay, that's right. Okay, I got it. Let us calculate
Yeah,
the
that was the part I was
energy.
confused.
Okay, yeah, energy, and then after that, the energy density. After that, the energy density, right? So first we calculate the
Okay,
energy,
thanks.
and then the energy density. That's what we did.
Thank you.
And that's the energy. And let me put them side by side. Thank you for pointing that out. Energy of a parallel plate capacitor, okay? And now, very important to that, here you go, energy of a parallel plate capacitor. And now, very important, okay? Even though I derive the energy density for a parallel plate capacitor, energy density of parallel plate capacitor, it happens that this formula also applies to any other geometrical configuration of a capacitor, okay? Okay, it happens that the above equation for the energy density is also the same for any geometrical configuration of our capacitor. Okay, any. So just a nice coincidence. Even though we use the formula for the parallel plate capacitor, this formula here for the energy density is also the same for any type of any geometrical configuration of a capacitor. So the energy density for a cylindrical capacitor is this one too. The energy density for a spherical capacitor is this one as well. Okay, we cannot prove that, but just trust me. Just trust me. Okay, it's very difficult to calculate for the other geometries. Okay, and here are the sections. Maybe we'll go back to the 19.7. Let's see how much time we have. Okay, it's an important experiment. And now I want to take attendance. Let's not forget, a student of mine asked me to postpone the exam, right, for 1 week. Right now, the exam is scheduled for 12th of March and it's being postponed. And I want to ask you if you're okay with that, with this postponement. Let's take attendance, lecture, and lab. writing here. Let's see, this one today is the 5th. Yeah, this one is gonna go elsewhere. So, okay. 6 lab 1. Okay, postpone exam. Abir Ahmad, are you there? I can see that Abir is connected here in our Zoom, but I don't hear from Abir. I'm gonna put a star in her name. Nestor Alvarado, are you there, Nestor?
Yeah, here.
Okay, can you postpone it, the exam? Postpone exam?
Yeah, that's fine.
Okay, good. Thank you. Monte Ambarcian.
I am here, Professor.
Okay, can I postpone the exam?
Yeah.
You're okay, postpone the exam, that's good. Hasti. Thank you. Hasti is not here. Hasti Amin. Yeah, not here. Okay. Isabella. Isabella Ballestero. No, Isabella Ballestero is not here either, right? Justus Boden.
Good morning, Professor.
Yeah. Is that okay to postpone the exam, Justus?
I'm more than cool with that, yeah.
Okay, thank you. Alexandra.
I'm here.
Yeah. What about the exam?
Yeah, you can postpone it.
Okay, thank you. Benjamin Carvajal. Let's see if Benjamin is here. Okay, let's put this on. It doesn't look like Benjamin is here. Brianna Carrillo. Are you there, Brianna? No, I don't see Brianna here. Next is Elizabeth Castellano.
Here.
Yeah, it's okay to postpone the exam, Elizabeth?
Yes.
Yeah, okay, thank you. And Natalia Cordoba. I don't see Natalia here. I don't see Natalia here. Let's go. Jacqueline Delgadillo.
Here?
Okay. It's okay to postpone the exam, Jacqueline?
Yeah, that's okay.
Okay, thank you. Jenny Diaz. I don't see Jenny here. Yeah, I don't see Jenny. Next is Valerie Diaz.
Here.
Yeah, you're there. And Yasmin, it's okay to postpone the exam, right?
Yes, please.
Okay, thank you. Yeah. Next, Juan Escalera.
Here.
Yeah, it's okay.
Yeah.
It's okay. Yes, okay, thank you.
Yeah, it's all right.
Okay, thank you. Bianca.
I'm here.
Okay. Let's see. It's okay to postpone the exam, Bianca?
Yes, it's fine.
Okay, thank you. Dana Gomez.
Here.
Yeah, it's okay to postpone the exam, Dana?
Yes.
Okay, thank you. Edwin Gonzalez.
Here.
Yeah, is that okay to postpone the exam, Edwin?
Yeah, that's fine.
Okay. Next is Ili Gonzalez.
That's right. I'm here. And yes, feel free to postpone.
Okay, thank you. Manuel Hernandez.
I'm here. And yeah, I agree to postpone.
Okay, good. Thank you. Next, Samantha. Is Samantha here? Okay, no, Samantha is not here. Faiz Hussein. No, I don't see Faiz. CJ, is CJ here? No, I don't see CJ. Luis Leal. Is Luis Leal here? Nope. Next, Amber Lopez. I don't see Amber. Okay. Arali Lopez.
Hello?
Yeah.
Yes, can you hear me? Yes.
Yes.
And feel free to postpone as well.
Thank you. Next is Genesis Lopez.
I'm here. You can also postpone the test. Really?
Thank you. Next is Mary Mikaelian.
I'm here and you could postpone the test.
Thank you. Ramon Olivares.
Here.
Okay. Can we
Yes.
postpone the test?
Yes,
Yeah.
please.
Okay, thank you. Taylor Forn.
I'm here, and you can postpone the test.
Okay, thank you. Next is Jeremy Pittman.
Yep, I'm here. And postponing school with me.
Okay, thank you. Stephanie Ramos.
I'm here, and yes, you could postpone it.
Yeah, okay. Thank you, Leslie Rios.
Yeah, hi, I'm here. You could postpone
Thank you. Jason Strait.
Here and yes, postpone.
Okay, thank you. Gema Torres Navarro. Gema Torres Navarro is not here. Okay. Let's see. Cindy. Yeah, Cindy is not here. Mohammed is not here. Okay, let's see how many students we have. 22. 24. We have more students. Oh no, just one more. Abir, are you there, Abir? Yeah, Abir. Okay. So it is 10:45 right now. Let's go for our break. And break 10:45 a.m. to 11 a.m. Okay. And then I see you in 15 minutes. Okay, welcome back. We need to continue with the lab that we started. Let's see. Another student coming in. Let's see where we stopped. Okay. They. Yeah, let's see. Let me get my spreadsheet here. Okay, that's lab 1. Okay, so at this point in time, did you finish? I want to know if you finished your significant figures, right? That's what I want to know. We have to do not just the significant figures, but we also have to do the CL, the confidence level. See here. Okay, CJ is here, right? Let me give you attendance here, CJ. Okay, and okay, since you missed, we are postponing the exam. Okay, CJ, we're postponing the exam by 1 week. So instead of the 12th, it's going to be the 19th of March. Okay, CJ. And let's see here. Let's remember. And let me get one of the spreadsheets. Oh. Lab 1. Okay, let me erase this thing here. I don't want this one. Okay, and I also have to revert it back to the previous format. Go, what else do I need to change here? Okay, so this one is okay. This one, do I have to do anything here? Doesn't look like. Okay, so what I have to do, I have to get another one. Okay. Okay, so am I sharing the screen? Yeah, I'm sharing the screen, right?
Yes, you're sharing your screen.
Okay, thank you. And okay, so I want to see what was the situation there with your graphs, right? Let's see, Abir, are you there, Abir? Let's start with Abir.
Yes. Hello?
Yeah, are you there?
Mm-hmm.
Yeah, and did you plot the equipotentials, Abir, of
Yes.
previous lab?
Mm-hmm.
All 5?
Yes, all 5.
Okay, good. So what else do we have here? Did you formatted the axis? Format the axis. Why is that?
Yes.
Yes, you did that too. Next is the
Yes.
second graph. Did you do the second graph?
I am almost done with the second graph.
Okay, so you're working on that, right? Working on the second
Yes.
graph. Okay, so let's go for Nestor. Hi, Nestor. Are you there?
Yeah, I am.
Okay, good. So did you plot all the five equipotentials?
Yeah, the 5 and then the second graph as well.
Okay, and okay, second graph as well. Did you put the trend line in the second graph?
Yeah, I did.
Okay. Did you formatted the axis?
Yeah,
Yeah, okay. Did you work on the units of the tables?
I did. I think I actually did the sig figs as well too.
I'm sorry, I didn't understand.
I said I got to the sig figs when I had to change the.
You got to the 6 figs. Okay, good.
Yeah.
Did you finish the 6 figs or are you still working on that?
I actually just finished it. I mean, I adjusted it the format so it could be from 3 to 4 sig figs and so on and so on.
Okay, good. So let's go. I'll get back to you about the CL. Okay, let me check with the other students. Let's see, Monte. Did you plot all the 5 equipotentials, Monte? I can't hear from Monte. Let's see. Here is going to be, I need to do something different. Lab, let's see. That should be 3, 5. Yeah, let me put this way. And okay, postponement. This one's gonna be this is gonna be 3, 5. The other gonna be a week ago, February 26th. Yeah, here you go. February 26th. Okay, now. Oh. Okay, so I'm gonna insert it here. Good. So that's gonna be okay. And you okay? So now let's go for Monte. Monte, did you already call Monte, right? Are you there, Monte? Okay, so I'm gonna put here an O for Monte. Oh, actually, it's gonna be a star. And Hasty, are you there, Hasty? Yeah, Hasty is not here. Next is Isabella. I don't see Isabella either. Let's go. Next one is Justus. Okay. Okay, just type there in the chat box, Justus. I want to know if you formatted the axis. No, wait a minute. The first thing is if you plotted all the five equipotentials. Did you do that, Justus? Okay. Yeah, just type there in the chat window. Just say yes or no. Did you plot all the 5 equipotentials? Yes. Okay. Good. All the 5. The next one is you format the axis of this plot. Yes. Okay. Good. Next, do you plot the second graph? There was a second graph. Did you plot it? Yes. Okay. Trend line, you get the trend line for the second graph as well? At the moment, no. Okay, so you're working on that, right? So continue working on the trend line and I'll get back to you later. Let's see, Alexandra. Is Alexandra here? I don't see Alexandra. Remistova. I thought I saw Alessandra, right? Yeah. Yeah, it looks like she left, huh? And okay, and Alexandra Remistova. Okay, I'm gonna write that down left here. Good. Benjamin Carvajal, are you there? Benjamin? I don't see Benjamin. Yeah, Benjamin is not here. Next. Okay, Brianna, you looks like you did everything, right? Oh, okay, last time we were talking. Did you finish the units, Brianna? Is Brianna here? No, Brianna is not here. Yeah, okay. Oh yeah, that's right. I'll get to you. Hang in there. That's right. Okay, so I want to know, Abir, did you, oh yeah, thank you for letting me know. You're working on the second graph, right? Yeah, okay, so here you go. I give you the attendance, okay? Now you have the attendance. Next. Brianna didn't reply. Let's go to Elizabeth Castellano.
Yeah, I'm here.
Okay, good. So let's see where did you, it looks like you finished the second graph, right?
Yes.
You got the trend line, right? And
Yes.
did you format the second graph?
Yes.
Yes, okay. Next, did you work on the units of the tables?
Yeah, I'm working on them right now.
Oh, you're doing that right now. Okay, working on that. That's good.
Yes.
Now let's see that Natalia. Natalia is not here, right? Let's see. Are you there, Natalia? No, she's not. So let's Jacqueline. Are you there, Jacqueline?
Yes.
Okay, so let's see how you're doing, Jacqueline. This lab is, I gotta change the date here. Fifth, okay. And I'm gonna blow it up better. Let me see. Okay, so I'm talking to Natalia, right?
No, Jacqueline.
Jacqueline, okay. Jacqueline writing here. Okay, good. So let me see here. Did you download the lab one?
Yes.
Okay, good. So did you plot the first graph with the 5 equipotentials?
Yes.
Yes, okay. So I'm gonna put 5 here. Next, did you format the axis of the plot?
Yes.
Okay. Next, did you plot the second graph?
No, I'm working on it.
Okay, working on that. Okay, good. I'll get back to you later on. Now let's see, Jenny. Are you there, Jenny? Jenny didn't come today, huh? Okay, so let me just mark it. Oh. Okay. Next, Valerie. Are you there, Valerie?
Yes, I'm here.
Okay, good. So last time you had formatted the second graph, right, Valerie?
Yes.
Okay, did you finish the units of the tables?
Yes.
Okay, good. What about the sig figs?
I believe so.
Yeah. Should I put
Yeah.
W here or should I put Y?
Well, I mean, I did last time, but I totally forgot if you said it was 2 or 3. But I did format it to at least
Okay,
2.
so you have your spreadsheet there in front of you, right?
Yes, I do.
Okay, do you see the sig figs there displayed there in your spreadsheet?
Yeah.
Okay, good. So I'll put Y here. And then I'll get
Okay.
to you about the CL, okay? Let's talk to Juan right now. Juan Escalera.
Hello.
Hi, how are you doing?
Good, and you?
Okay, good too. So last time you had finished the units, right, Juan?
Yes.
Okay, did you finish the sig figs as well?
I'm doing it right now.
You're doing that. Okay, so let's put W for working. Now, Bianca. Are you there, Bianca? I don't see Bianca here. Okay, Bianca was here, so it looks like she left. Okay, thank you, Justus. I'll get back to you, okay? I'm gonna put it left. Okay, next. Dana. Hello, Dana, are you there?
Yes, I'm here.
Okay, good. So did you download the spreadsheet, lab 1?
Yes.
Okay, good. Did you plot all the five
Yes.
equipotentials? Yes? Okay.
Yes.
Okay. Did you formatted the axis of this first plot?
Yes.
Okay. Second graph, did you plot the second graph?
Yes.
Okay, the trend line, did you get the trend line?
No, I'm working on it right now.
Okay, so let me put working here. And next is going to be Edwin Gonzalez. Are you there, Edwin? Hello, Edwin, are you there? Looks like Edwin is away from his computer. Let's go to Ellie Gonzalez.
Yes.
Okay.
I ended up finishing the units and I've done the sig figs.
Oh, you've done the 6 fig. That's good. And now we're just waiting for the CL, right?
Correct.
Okay, so let me finish with the other student, then I'll get back to you, okay? Samantha is here. No, Samantha is not here. Faiz is not here. Next one is CJ. Okay, CJ is here. Hello, CJ. Edwin. Okay, thank you. You're working, Edwin sent me a message, right? You're working on what? The sig fix? Edwin? Okay. Okay, so Ellie, on the sheet. Okay, okay. So let's see. Next is Manuel. I'm all done, waiting for the next part. Okay, thank you, Manuel. And let's see, CJ. What happened to CJ? Okay, you're working. Okay, but where are you working, CJ? Did you download the first thing? Did you download the lab 1, the spreadsheet for lab 1? Yes. Okay, good. Did you plot the first graph? First graph has 5 equipotentials. You plot all the 5 equipotentials, right? On the data, yes. Okay, good. Okay, so did you format the axis of this first plot as well? Just the first. Okay. Yeah, just the first. Good. The second graph, did you plot the second graph? Oh, you're working on the second. Okay, good. So now let's go for the next one. Let's see, Genesis. Genesis sent me a message, right? You're working on okay. Genesis. Well, okay, CJ, let's see. Luis Leal is not here. Amber. Last time, Amber is there? Amber is not here. Okay, let me put 0 here. Next, Elizabeth, Adelie.
Yes, I'm here.
Okay, let's see. You didn't come last time, right, Adelie? Did you download the lab number
No, I
1?
didn't. Yes, I did.
Okay, good. Next, did you plot all the 5 equipotentials?
Yes, I'm working on the sig figs
Okay,
currently.
we're going 6 fig. Okay, so let's go there. 6 fig. Do you need any help with the 6 figs?
No.
Okay, good. Okay, now it's Genesis. Finally, I got to you, Genesis. Here you go. Did you plot all the 5 equipotentials, Genesis?
Yeah, I just need the 6 fig.
Okay, so you're doing the 6 figs, right? So let's go there. You're working on the 6 figs or 6 figs or?
No, just working on it. That's my next step.
Next step. Okay. So let's put W here for working on the 6 figs.
Professor.
Yeah. Who is that?
I don't know if you saw my message. I said I was here for Edwin. That I'm working on it.
Okay. What's your name?
Edwin.
Edwin. So let me see here. Edwin. Oh yeah. Okay. Good. So and you are working on what? On the 6 figs, Edwin? Or in the unit?
Yes, I did the units already. Yeah.
Oh, you already did the unit. Okay, that's good. Thank you. So here you go. Genesis. Where did I stop? I stopped at Genesis, right? Good. So let's Mary. Hi, Mary.
Service ever created? Was it
Yeah,
1881?
Let's see. There are 2 students talking at the same time. Hang in there.
And
Hi, Mary. Go ahead. What did you say, Mary?
I was saying I finished the sig figs.
Okay, you finished, and you're just waiting for the CL, right? So
Yes.
okay, good. I'll help you out with the CL very soon. Ramon Olivares, are you there, Ramon?
Yeah, I'm here, Professor.
Okay, did you finish the units?
Yes. So I finished table 1-1, 1-2. I'm on 1-3.
Okay.
Working
So
for or looking
the
for
unit or for
CL.
the sig figs?
For the data and results.
But let's see. Are you talking about the significant figures or the units?
Well, the sig figs we did last week, right?
Oh
I'm not
well, last week you were working on the units, right? That what says here. You were working. Did you finish
I
working?
finished those. Yeah.
Okay, and now you're working on the sig figs, right? Significant figures.
I think I finished them. That's why
You
I'm a
finished
little.
them. Okay,
Yeah.
so you should know how to do the CL, right, Ramon? Because you were my student before, right?
Correct.
Okay,
With the
good.
and then
Okay, so work on the CL. Let's see, Alexandra is coming. Next, Taylor. Are you there, Taylor?
Yeah, I'm here.
Okay, good. So last time you were working on the units. Did you finish?
Yeah, I finished it.
Okay, good. What about the sig figs?
Yeah, I did that too.
You did that too. Okay, and you know how to do the CL, right? The competence level. Okay, good. So I'm gonna put that you're working on that, right? Did you finish the CL already or not?
Yeah, I finished it.
Oh, you did. Okay, good. Yeah. Are you working in a group, or do you have any other students that you have been working with in this lab?
No.
No,
I mean, I
right?
have a group.
Huh?
I have a group, yeah.
Yeah. Okay. So share whatever you know about the CL with the other students. Okay. So you can help them getting ahead. Okay. So let's go to Jeremy. Jeremy, are you there?
Yep, I'm here.
Okay. Did you plot the second graph, Jeremy?
Yes, I'm working
Okay.
on the sig figs now.
Okay, good. Trend line, you did the trend line, you formatted unit. Okay, so you're working on the sig fig. That's good. Stephanie. Hello, Stephanie. Let's see, Stephanie here. Yeah, Stephanie is here, but she's not answering me.
Sorry, I'm right here.
Okay, good. Did
I'm
you
having like difficulties here with my internet. Sorry.
okay. Did you format the second graph?
I'm still on the second one. I feel like I had to start over because it didn't save from last time. I don't know why,
What a shame.
but I'm redoing the second one now.
Okay, so I should put it working right in here?
Yeah.
Okay,
Yeah.
good. So let me take it out. Good. Next is Leslie Rios. Hello, Leslie.
Hi, I did everything. I'm just working on the sig figs right now.
I work in the sig fig. Okay, good. Jason Straight.
Yeah, I did the sig figs.
Okay, you did the sig figs and just waiting for the CL, right?
Yeah.
Okay, do you know how to do the CL?
Is it the same as how it was last
Yeah.
semester in 06? Yeah, I know how to do it.
The same as last time, okay?
Okay, yeah, I'll get to that then.
Okay, good. So let's see, Hema. Hema is here. Doesn't look like. So let me put and Elizabeth. Okay, good. Now let me fill you in on the CL. Okay, so whoever is waiting for the CL, already know how to do that. Okay. So what we are going to do here is the following. Here you go. You're going to plot the CL that we're talking about. This is the CL for the second graph, okay? You cannot get the CL for this other graph here. There's no CL there for you to work on. But you can work on the CL for this second graph, right? The first thing that you have to do is to plot this graph. Most of you have already plotted this graph, right? It's going to be a straight line. Do you see that? Add trend line, display R squared, display equation chart. Here you go. So what we have here, we have V here in the vertical, and we have X position here in the horizontal. That's exactly what we had predicted in the theory, right? For two parallel plates, the electric field is uniform, but the electric potential is going to be linear. It's going to be a linear equation. It's going to increase linearly, okay? And what do we have to do to know? Well, it's the following. The slope right in here of this equation is going to be exactly the electric field, okay? So this value that you have right in here, 77.859, is going to be the electric field strength. Make sense? Okay? So is that, so just go ahead, whatever slope you got there, write the value right in here in this table 1-4. Okay? Is slope and the electric field, and put the unit as well. What about the CL? What about the CL, right? You're going to need this graph here for the CL and work with this table as well. First thing you have to do is to write down the number of data points. Okay? 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. So you put it 5. 5 data points. That's what N is all about. You're going to need this value to find out the CL. I want you to write down the equation as well, the regression equation. This regression equation right in here. I will copy and paste it here. Oops, didn't work. Let's try it again. Let's see if it worked now. Yeah, it's working. It looks like it did work. Yeah, equation. See that? Copy and paste. Don't put double, okay? And okay, that's V against X, right? So what you have here is correct. And then you gotta write down the R square as well. I'm gonna copy the R square value and paste it here. Oh, didn't copy. Let's try it again. Let's see. Let's try it again. Yeah, I didn't copy for some reason. I'm gonna type it. 0.9987. And now you are going to need those two numerical values, n and r squared, to find out the boundaries of your CL, the lower value of your CL and the upper value of the CL. To do that, you have to go in that table that I posted in Canvas, okay? Let's go there. Canvas. In the Canvas course, log in, Canvas. We go. Course. Physics 2, 17911. Right in here, confidence level. Make sure you download this PDF file. Download. You're going to need this table for the rest of the semester. The students who took the course with me, Physics 6 with me, already know how to use this table, right? But most of you didn't take the course with me, didn't take Physics 6 with me. So I have to cover that with you. Here you go. Here's my table of CL. Critical values of R squared for different confidence levels. Okay, this is the confidence level is a parameter in statistics. That's what the confidence level is all about. It tells you how close. Let me write that down so you don't forget, right? Here you go. Let us talk about the confidence level. Lab 1. Continuation. Confidence level. Okay. First thing, 1. Download the PDF document in Canvas entitled Confidence Level. Okay. Note that this document relates, has a column. This document has a column, has the following cells. Okay, let's put it this way: following cells. 1. In the extreme left, it has a column with the number of data points n. Okay. Here you go. I'm talking about this column right in here. I want you to become familiar with that. This column here, you can ignore this other column, okay? You can ignore this other column. I'm going to redo this table, eliminating this column here. It's not necessary to be there. Okay? So this table has this column with the number of data point values in your table, in your graph. And, okay, at the top, second row from the top, you have your CL, confidence level, values, right? And the CL is this one right in here. And just like the DF, you can ignore this other column. We're not going to use it. Okay? I'm going to simplify this table. And I'm going to erase the DF and the alpha. And then you have everything else. Everything else is what you see right in here. Okay? Everything else you have that, you know, and see the body of the table. Everything else, right? These are the critical values of the determination coefficient R squared. Okay? That's what you have to know. If I were to make a drawing of this table, and I'm going to do that for you. Let's see. I'm going to do it right here. If I were to make a drawing of this table like that, here's the table. Okay. We are going to have, here you go, CL here at the top. You can ignore the alpha, right? CL here at the top. It starts at 0.95. I want you to understand this table. That's why I'm doing that. 0.95, 0.99, 0.99. Further down, 0.999, right? And choose the other one. 1, 2, 3, right? 0.99999. It's a bunch of nines, right? 1 minus 10 to minus 7. 1 minus 10 to minus 7. That's superscript. Okay. Here is 1 minus 10 to minus 3, right? 1 minus 10. Yeah, 1 minus 10 to minus 3. Oh. Let me put it outline. Yeah. Okay, so that's the rule that I mentioned to you, right? And then there is also the column that I mentioned to you. The column with the values of n. Like, oh. Okay, n. Ai. We start with n equal to 3, 4, 5. There's a reason for that. 9, 10, and so on. Okay? Here you go. 3, 4, 5. Again, like I told you, you can ignore this column here. It's not CL. CL is not in the horizontal row. in the vertical row is something else that we call numbers of degrees of freedom. Degrees of freedom, which is n minus 2. See that? It's exactly n minus 2. The alpha you can also ignore. The alpha is related to the CL, is 1 minus CL. See that? 0.05 is 1 minus 0.95. 0.01 is 1 minus 0.99, and so on. Okay? And now what do you have here? In the whole body of the table, you have the values R squared. And I'm gonna make it very large, R squared. I'm gonna make it even larger than that. Let's see, 200. Yeah. Oh, no, it's too much. I'm gonna make it larger. 500, let's see. Yeah, it's too much. 400. Let me get that. Yeah. No, it's too big. Let me decrease to 300. Yeah, okay. That's how I represent that table. I like to represent that table, okay? And in the vertical column, CL in the horizontal row, and in the body of the table, R squared. The idea here is to find what are the values of CL that that is around the CL that you are going to find, okay? That's what it is. So you won't be able to find the exact CL. You won't be able to find the exact CL with this table. Let me write that down here for you. You, very important, will not be able to find the exact CL for the data you have, for the data of your second graph, right? Of your second graph. Instead, you will be able to find only the bounds. Only the bounds of your real CL. Okay? And how do we do that? Right? To find these bounds, the bounds, upper and lower bounds. Upper and lower bounds. To find these boundaries, right? You have to do the following. You will need to do the following. Here you go, one more. Find the number of data points in the table, on the table. Okay, so let's see here. What value is for each field? Okay, Manuel is asking me, is it recording? Good question. Let me see if it's recording. Resume recording. Okay, good. So it was recording, Manuel. Thank you anyway. Okay, so first start with the number of data points. Start with the number of data points on your table. In this case, for lab 1, n is going to be equal to 5. Okay, so here you go. Here's the table. n equal to 5, you know, use your CL, you're going to find, yeah, that's right. The value of the E field is the slope in the equation, in your linear equation, okay? Here you go. That's what you do. N equal to 5, you're going to look for the boundaries of your CL from somewhere, you know, one of those, you know, using, not that the CL is going to be one of those numbers. No. You're going to use those numbers, one of those numbers, to find out your CL that's going to be here at the top, right? That's how it works, okay? That's the first step. Second step, locate your R square. Locate your R square along the row on the table. Okay? So let's see what's my R square. I have to go, I use here for the group number 1. R square is 9987, 0.9987, right? So let's look for 9987 in this table. You know, here we have 0.84, 0.65, 0.84, 0.94, 0.98, 0.994, right? We want what? 9987. Let's take a look again. 9987, okay. It's not 994, 9983. Okay, 9987. Oh, sorry, this one here. 9987 is going to be between those two numbers, right? N equal to 5. 9987 is greater than this value and less than this value, okay? And now that we located where your R square is located in this table, in this row, you just read the lower bound of the CL, which is this number, and the upper bound of the CL, which is this number here, okay? With this table, again, I'm going to repeat, you cannot find the exact value of the CL, but you can find the boundaries where it lies, okay? And that's going to be exactly the two numbers that you're going to write down in the bounds of your CL here in this table. Here you go. Upper bound or maximum, right? And lower bound or minimum. Let's go back there again. 1 is going to be 1 minus 10 to minus 4. 1 minus 10 to minus 4. And the other is going to be 1 minus 10 to minus 5. We're not done yet. We are not done yet. Right now, I just typed what is supposed to be a number. Okay, but Excel does not recognize those values as number. In order for Excel to recognize those values as a number, what you have to do? You have to put an equal sign on the left side. Okay, here you go, equal sign here, equal sign here. And now you have the lower bound of your CL and the upper bound of your CL. Your actual CL is going to be a number between those two here. Okay? That's what you have to know to complete your table. Okay? Is that clear now? Just, you know, you have to learn how to use this table. That's all. Okay? You will always read the CL here at the top. Right? And you're going to use the rest of the table to find out the CL. And what is the CL? Okay, let me write down what the CL is. The very important, locate your R square value on the row, along the row, along the market, along the row on the table, right? For n equal to 5. For n equal to 5. your R square should be between two different R squares on the table. Okay? One is going to be the lower bound, and the other the upper bound of your R square. You're not done yet. Next, move upwards on the table to find the lower and upper bounds of your CL. That's how you do it. Let's see, am I missing anything here? No, Manuel, B part is going to be the intercept, okay? M is going to be the slope. M is the slope, B is the intercept. Okay? So if, okay, so going back to my data sheet here, right? Here you go. My electric field is going to be this value here. The slope of your graph. This number here is not the slope. This number here is the intercept of the graph, okay? So that's going to be the number that you log right in here, both for the slope and the electric field. So just by doing this simple experiment, we can find out what is the value of the electric field in that configuration, in that electrode configuration, okay? 11:55 right now. I want to take a break. And man, we're not going to be able to do lab number 2, huh? Let's see if we can do lab number 2. Hopefully there will be some time left for us to do lab number 2. I'm going to, here you go, break 11:55 a.m. to 12:10 a.m. Let's see, why is the number so big? Which number are you referring to, Ramon?
So when I put in my CL min and max, I don't know what's happening after I put the equal sign. Like I'm getting like 38,000.
38. Okay, most likely you'll be typed in the equation there. Okay, check it. Maybe you forgot to put minus here. Is that check there your number? Okay, maybe you.
I put my like -6. I put it as a superscript. Does that affect it?
Oh, you put a superscript. Okay, don't put a superscript. Excel doesn't recognize a superscript as an actual number. Okay.
I just use the up arrow.
Yeah, I just use this hat, right? The hat symbol. Okay. Yeah, the hat symbol is for power. Hat symbol is for power, right? 1 minus 10 power of -4. Okay.
Yeah. Thank you.
Okay. So let's go for our break. I'll see you in 15 minutes. I will pause the recording. Don't forget to remind me. Okay, I'm back here. And let's see. There you go. So here is the tables, right? Don't forget to fill up the units here. You have to, you already can fill up the units on those two. And in order to find out the units right in here for those three, I need to give you the equation for those three quantities here, okay? Here you know the unit, what it is. Here you know the unit. All of those, they're kind of straightforward, right? The secret now is what the unit for those three. For those three right in here. In order to find out the unit, you gotta look at the formula. Okay? What you have here is the standard deviation. The standard deviation of those 1, 2, 3, 4, 5, 6 measurements for the exposition. For the exposition, okay? The next standard deviation that you have is for the measurement of those other positions for 4 volts. Okay? And so on. Standard deviation for the exposition for the 6 volts, standard deviation for the exposition of the 8 volts and 9 volts. Now, the next question that you've got to ask yourself, what is the equation for the standard deviation, right? You must know the equation for the standard deviation before you fill up the unit that will go here. Let's start with the standard deviation, right? And then we'll talk about the other two. Okay? So here you go. The standard deviation is a statistical parameter. So here you go. There are several statistical parameters, right? The very first statistical parameter that we learn, okay, one. The very first statistical parameter we learn, most likely in first grade, right? Is the average. That's the very first one we learn. And the equation for the average is what? The equation for the average is, you know, well, put it, let's say we're taking the average of n different numbers, right? The equation for the average of n different numbers is going to be the summation of those n different numbers divided by n. Let's use capital N. That's the equation for the average. The average we usually represent by the letter X bar. That's how we usually represent the average. That's easy, right? But there are more. And here you go. And what else do you have to know? Here you go. The X average is exactly this parameter right in here. And here's the same thing, right? That's the V average, the voltage, the average of the voltage. Okay. So what's the unit of the average of a given number, right? Of a given set of numbers, right? What's the unit? Okay, the unit for the average is going to be the unit of each number. It's going to be like that. Okay, it's going to be the unit of this thing that's here right in here. The number n has no unit whatsoever. It's a unitless number. Okay. So instead of putting here in this line, I'm going to put it right in here. So you can see better those numbers. Okay, here you go. Now it's cleaner, right? Easier to see. And then we keep on doing those. We keep on operating with those square brackets. No, we can operate the square bracket in the following way. We can put the square bracket inside the summation sign. And then we apply the distributive property of the square bracket, which is going to be, the unit of xi divided by the unit of n. Okay? Here you go. Like that. Oops, don't forget this n here. The capital N is a regular number. And because it's a regular number, each unit is going to be unitless. The unit of a regular number is going to be 1. Is unitless. Is a unitless unit. A regular number is a unitless unit. Okay. What about the unit of the xi, right? The unit of xi in our case for the position of the data point is going to be the meter. Okay. And when you do all the math here, you get that the unit of the average is going to be the meter. You repeat that for the voltage, and you get something like that as well. Here you go. Capital V, right? Capital V. Capital V. We're still doing the average, right? We're not doing the standard deviation yet. Capital V. The unit of capital V is going to be capital V, the volts, right? And volts. Now let's do the standard deviation. Of the standard deviation of a given set of numbers. Okay? In order to do that, you're going to need the equation for the standard deviation. So you can evaluate what that would be, right? Here you go. That's the equation for the standard deviation. Is the value that you measure, the first value that you measure, minus the average. Okay? I put AVG without the X bar, right? Let's put X bar there to keep it consistent with the notation that I am using. Here you go. X bar here, X bar here, X bar here, right? X bar here, just to keep it consistent. Okay? See, we have a square root outside, right? We want to find out the unit of the standard deviation. We proceed with the same steps that we did before for the average. Unit of the standard deviation is equal to the, I'm gonna skip this one here and put just, okay. See, we have a square root, don't forget. Just like before, we can put the bracket there inside. We're not calculating a numerical value in this case. We're just calculating the unit in this case. Okay, another step, distributive property. All right. Right? Okay. The unit for a number, a regular number, is going to be the unitless unit. And now we gotta get the unit of something squared. Okay? The unit of something squared is going to be the square of the unit. Right? But don't forget, we still have a square root here. Still have a square root here. You know, when you sum all those units, you still get the same unit at the end, right? And finally, the standard deviation will have, of a given parameter, we have the same unit of the parameter itself. Of a set of parameters, right? You have the same unit of parameter itself. Okay? Standard deviation. Standard deviation, by the way, is represented by the Greek letter sigma. This symbol that you see there is the Greek letter sigma. So you have the unit for this guy here now. Now you do the same for the other two, okay? I'm not gonna give you the result, the final result, but you can figure that out by yourself. What's sigma x? Sigma x is the standard deviation of the mean. Okay, what's the unit of the standard deviation of the mean? Okay, that's the name of that parameter there. And we represent it by sigma subscript x. 1225. Am I missing anything here? Let's see. Doesn't look like we'll be able to start lab 2, right? Okay. Okay, the definition of sigma x is the following. Is sigma over square root of n. So the unit of this number is going to be the unit of this other number here. And then finally, both sigma and sigma x are the, here you go, both the, let's put here, the standard deviation, the standard deviation is a measure spread of your measurements. In general, you want a standard deviation much less than the average. Okay. Let's see if you're getting much less than the average. I want you to check that with your numbers as well, okay? Oh, and by the way, notice that those are in red, bold-faced red, okay? Those quantities that are in bold-faced red, in red bold-face, do not require significant figures. Those numbers here do not require significant figures, okay? Let's write that down in terms of numeric parameters. That's easier to read. Okay? Look here, we're getting 0.0034, whereas the x average, right, is greater than any of those other values. Okay? Is the x average is what almost 10 times more than its standard deviation. This one here is more than 10 times the standard deviation, its standard deviation, right? And so on. Yeah, 10 times, more than 10 times, right? So that's the type of ratio that you want between the standard deviation and the other numbers. Now, the standard deviation of the mean, okay? The standard deviation of the mean, standard deviation of the mean is usually used as the error of your measurement. Okay? And what do I mean about that? I mean that whenever you write a given measurement, right? In the case of X average, how you should report the X average. The X average is usually reported as, with an error there. Here you go, X bar plus and minus sigma X. That's how we usually report a measurement, with the average value plus and minus the sigma X. Finally, we have the other parameter that I listed in there. The unit of this other parameter is a little bit trickier. Okay, so let's see here. Someone's trying to get in. Yeah. What's gonna be the, okay, so that's gonna be easy, right? Sigma X, okay, the ratio. That's an important ratio because it gives you an idea. Or, okay, didn't do it. Restart, continue numbering. It's not numbering. Appropriate set numbering value 5. Okay. Now you should have it. What's the unit of sigma X over X, right? Average. What's the unit of sigma X? I'm gonna put it here. Sigma X over X bar, like that, for a given set of numbers. Okay, you do exactly what we did before. Okay, so here you go. The square bracket of that is going to be equal to the square bracket of sigma X divided by the square bracket of X bar. Right? And now you finish by yourself. This one is a little bit tricky, okay? But let me do that for you. But you're gonna find things like that before, as in the other labs. Okay, not before, but you're going to find things like that in the other labs. Okay, so the unit of sigma X is meter, right? The unit of the X average is also the meter. And then what do? Meter cancel out this meter, and the unit of that parameter will be unitless. And then you report between you report it as 1. Okay, it's the unit there. What time is that? 12:33. You have 20 more minutes to go. Okay, so it looks like we did, don't forget the units too, right? Units of the slope, units of the electric field. You can do dimensional analysis for that. Let's see how we are doing there. Going back to the spreadsheet here. Abir Ahmad, are you there? Okay, Abir Ahmad, looks like Abir Ahmad left. Okay, and Nestor Alvarado.
Yeah.
Did you get the CL already, Nestor?
Yeah.
Okay. So looks like you're done, right?
Yeah, basically. Is that it? If it's the CL, then that's it.
What did you say?
If the CL is the last part, then yeah, I finished it.
Okay, you did, right? Okay, so let's see. Let's go to Monte. Monte, are you there? I can see Monte here, but looks like Monte is away from the computer. Oh, okay, good. So did you plot all the five equipotentials, Monte? Oh, you're finished. Okay, finish mean format axis, second graph, right? Trend line, format of the trend line units. Oops, my gosh, I'm putting the wrong one here. Why, right? Okay, did you get the TL2? Okay. Now, okay, thank you. Hasti, are you there, Hasti? Hasti is not here. Isabella, I don't see Isabella. Okay, what about Justus? Did you finish the trend line, Justus?
Yeah, I basically caught up with everything so far.
Everything?
Yeah.
Including the CL?
Yeah.
Okay. So let's go, Alexandra. Hello.
I did everything too.
Everything too? Okay. Why? Okay. Even the five, okay. Next is Benjamin. Are you there, Benjamin? I don't see Benjamin. Yeah, I don't see Benjamin here. Brianna. I don't see Brianna here. Elizabeth Castellano.
Yeah, I caught up with everything.
Everything? Okay.
Yeah.
Next, Natalia. Natalia is not here, right? Next is Jacqueline. I don't see Jacqueline here. I'll put it left. Jenny Diaz. You finish, Jenny? Jenny's not here. Okay. Next, Valerie Diaz. Did you finish the CL, Valerie?
Yes, I did.
Okay. Do you have any questions? Do you need any help?
I don't, but thank you for asking.
Okay. Juan Escalera.
Yeah, I think I did the CL right.
Okay, good. So you finished. What about Bianca? Bianca's not here, right? She left. Dana, did you finish everything?
Hi. Not yet. I'm on the sig figs.
Sig figs. Okay, so I'll put it here. Sig figs. W. Next, Edwin Gonzalez. You finish everything?
Yeah, I finished everything.
Okay, thank you. And Ellie Gonzalez.
I finished with the CL.
Okay, good. So you finish everything. And 2 more minutes to go. Manuel Hernandez.
I finished the CL2.
CL2. Okay, good. Samantha is not here. Faiz is not here. CJ. Hello, CJ. Okay. Okay, I'm not hearing from CJ. I'll put a star here. Luis Leal is not here. Let's see, Amber is not here, right? Elizabeth Lopez. Two Elizabeth, right? One Lopez and the other Elizabeth Castellano. Oh. Is Elizabeth Lopez there? Well, I put it left. Genesis. Are you there, Genesis? Her middle name. Oh, her middle name is Elizabeth. Oh, Adelie. Okay, okay. Thank you. Well, but what happened to her? She left, right? Yeah. Okay, thank you for pointing that out. Genesis. Okay, here I'm working on CL. Okay, working on CL. Good. Mary, Michaelian.
I finished.
Finish everything. Okay, good. Ramon Olivares. All done and submitted. Okay. And Jeremy Pittman. Don't forget this lab report is due next week. Okay.
Yeah, I'm here.
Okay, did you finish everything?
Yeah, I'm still working on it.
Working on what? On the CL or the sig figs?
Yes. Well, the sig figs. I'm taking my time right now.
Oh, okay. So let's go for Stephanie. Stephanie Ramos. Stephanie, no, it's not here. Okay, well, I put here that she left. And Leslie?
I'm done with the sig figs. I'm just working on the CL.
You're going, okay, I'm done with the sig figs, working on the CL. That's good, thank you. Jason Straight?
Yeah, I did my CL.
You did? Okay, good. And everything else. Okay, so 12:40. Let's see if there's anything else. Abir's left, right? Okay. So yeah, we're done. Okay, let's I'm gonna upload lab number 2 before we meet again. Let me write that down here. We're done with lab 1. The spreadsheet is due next week, March 12, 25. Okay. Next week we start lab 2. Next week we start lab 2. Okay. And let me fix here okay, lab 1. Lab 1. And okay, so we have changed the date for exam 1. Okay, that's going to be next week. Here is gonna do lab 2. Electric field 2. Which is going to be very similar to the first lab. And do you have any questions?
Yes, could you go back to the spreadsheet quickly, please? Or before you close it.
I'm sorry, I didn't understand.
Can you go back to the Excel sheet, please?
To Excel, okay. Going back to the Excel, here you go. What do we need here? Is that what you want?
Yeah, I just thought you wrote units for table 1-2.
1-2. That's table 1-2 here.
Oh, but I guess you didn't, so that's fine.
Okay. What we need to put on table 1-4. Table 1-4. Okay, table 1-4. Okay. You did put the numerical value of the slope, right? The slope of the second graph. That's straightforward, right, Elizabeth? You have the slope here. You write down this value there. Right in here. And then you put the unit. You put the unit. Okay? You do dimensional analysis. You plot the V against the position. Okay, so the slope is going to be what? The rise, the unit of the rise, that's volts, divided by the unit of the run, volt per meter. Okay, so that's what you have here for these two cells. The electric field is the same as the slope value. Okay, the electric field coincides with the slope. So whatever you have here, you just copy and paste here. Okay, that's what 1-4 is all about. Okay, and okay, so we're done. Okay, I have office hours right now, and if you want to hang around, ask any question, I'll be here for another 45 minutes. Okay.
Thank you, Professor. Have a good
Thank you,
one.
Professor. Have a good one.
You too. Bye-bye.
Hello, Professor,
Yeah.
you there?
Hmm?
So we still have to figure out. I haven't figured out the Wiley Plus thing.
Okay.
I don't know.
You can call. I'm going to try to call Anthony. Did you call Anthony there at LA Harbor?
Yeah, they gave me a hard time.
Really?
Yes.
Oh, you treat me so well. Let me see. Maybe that's because I'm instructor, right? Let's see. Let's see if I can get. But let me fix this thing here first, and then you call him. Exam. Okay, resistance measurements. Let's see, electric circuits. Let's put this one, electric circuit 2 here. That's the one I need to fix. Monday, Wednesday, Monday. Let's see, this one be filled right in here. Okay, this lab 3 is going to be, my goodness, on the other. Then. Single, this one gonna go elsewhere. The Chavez Day. Lab 8. I'll have lab 7. Lab 6. Lab 6. Lab 5. Lab 5, Lab 4. That's the one. Well, what's happening here? Oh, yeah. Lab 4. Okay. Oh, wow. Jesus Christ, what did I do? Gotta do it all over again. 8, 7, 6, 5, 4. Okay. Okay, good. Okay, so I got it. Lab 1. Okay, good. So I finish here. I will save that. Now, let me call them here. Do you have the phone number of the bookstore, LA Harbor Bookstore? Hello, Jeremy?
Yeah, I'm here. I'm sorry.
Okay.